So they have codimension, complex codimension 1 or real codimension 2. So that would be okay. let me like use Poincare duality and roughly use this notation that the element dual to second cohomologies. So therefore here we can just to be sure, like delta functions on this hyperplanes, and that would be like a pairing, or if you want, that would be integrating with beta delta function of HP. So in kind of practical terms, so when we have a tropical curve, so tropical curve is some, okay, so tropical curve of genome 0 is some tree, and this tree has some leaves, and leaves, as we say, they are kind of edges that go to infinity, and then these edges, as they go to infinity, they will intersect compactified hyperplane somewhere in infinity, and kind of curve class is essentially a collection of numbers, collection of integer numbers of which hyperplanes and how many times each hyperplane is intersected by the semi-infinite edges. Okay, so that would be theorem 1, which is turning tropical Gromov-Witten invariance into some correlation function in a certain higher topological quantum mechanics, and then hopefully we will have time to talk about theorem 2, which will be, so we will take as sum over this tropical Gromov-Witten invariance with curve class beta, weighted with q to the beta, and we will see that apparently this sum, even though that looks like way more complicated object, that each individual term is already correlation function, that is itself is the sum of amplitudes and so on, but it turns out that this summation kind of simplifies, and it can be expressed in the following way, that it is a correlation function, but of just n objects. So correlation function of n states, but in some kind of new HTQM. And this simplification is kind of an essence of tropical mirror symmetry, that this summation over various degrees, like here, the tropical Gromov-Witten invariant, as we will see, it kind of depends on two types of data. It depends on which observables we use, and it also depends on a curve class. And HQM kind of takes these two bits of data as a different kinds of inputs. It's like two types of states. However, as we perform summation of a beta, it turns out that the contribution over all these states corresponding to compactifying divisors is sort of becomes just a deformation of HTQM into some family that is now parameterized by this data. So that's why I call it Q upper script X. So it is family of HTQM parameterized by a choice of our toric variety X. And similarly, we deform these states to get the states in a new HTQM, and this endpoint correlation function just equal to this tropical Gromov-Witten invariance summed over all degrees. And I think on the next lecture, which will be our final lecture, we will prove the third theorem is how to turn this expression into correlation function in Landau-Ginzburg cycle theory. So that's the plan. So now let us proceed with kind of proof. Or before even proof. So here I sketch theorem 1. So let me the details of theorem 1. Before we go to proof, I need to explain what are all the states are and how they are constructed. Okay, so let us recall the HTQM example from 2 lectures ago, and this HTQM example was the following. So for a vector space, we choose a kind of differential forms on on a toric variety X that are invariant under U1 to the capital N action, capital N, complex dimension of X. So that's our vector space. So then, okay, and we should enter it with n-dimensional integer lattice. So kind of states here. So vectors in V. So we use this Bryan ket notation. So in ket notation, it is differential form to the pair, differential form, and integer vector. So that is U1 to the n invariant differential form and integer vector. So now, kind of Q acting on state omega m was the run differential on X acting on form omega, and vector field remains the same. So then for G plus differential, we do the following thing. So we take this vector field M and construct a kind of radial vector field Rm here, which is constructed in the following way. So we say that in kind of standard basis, d over dr1, d over drn, this vector field has kind of coefficients equal to components of this vector m. So let me use different notations. So I can write it like this, or to be very explicit. So it is a vector field that has this form m1 d over dr1 plus m. Okay, so m is a vector, so I should put d over dr. So that is kind of my vector field, and then what we do, we substitute this radial vector field Rm into our differential form omega, and keep the vector unchanged. So in a similar way, we define G minus, but instead of radial vector field, we can construct an angular vector field in a similar way. So we take kind of canonical basis in angular directions, and kind of say that this vector field has components m1 to m capital N in this basis. So here we will just substitute this angular vector field into our differential form omega and keep the vector unchanged. And now, in order to satisfy Q and G minus, so Qx as the Dirac differential, G minus x as the substitution of some vector field. So it's not surprising that the anti-commutator will act as the derivative along this angular vector field. However, our choice working with U1 invariant forms explicitly implies that the Lie derivative with respect to kind of any basis vector field d over d phi k for any differential form 0. So this thing is just 0. So therefore, choosing this U1 invariant form is a way to satisfy this condition that Q anti-commutes with G minus. And but in case of G plus, So we have kind of v derivative acting in radial direction, and we keep it and call it Hamiltonian. And that is our Hamiltonian. And this Hamiltonian has some nice properties that we require. That exponent is defined, okay, and what about remaining data? So we have a pairing, so for pair of vectors omega 1 and 1 and omega 2 and 2. So the pairing works in the following way. So first, we check that the sum of these integer vectors is 0. And if it's not 0, so then we just say that this pairing equal to 0 on this pair of states. But if it is 0, so then we take the product of these two differential forms and integrate over it. So that is the way to produce kind of number in the case when integer vectors add up to 0. And the kind of final object is multiplication. Once again, take a pair of states. Multiplication is defined in the following way. So we have a wedge product on differential forms. So therefore, in kind of differential form part of this state, we put a wedge product, and in this integer vector part, we put some integer. So that this example, HGQM example, I think in our papers we call it A-type HGQM, to kind of distinguish from this other HGQM that we will call B-type, and hopefully we will get to it later today. Okay, so we have this A-type HGQM. So now, that defines like these brackets. So that defines amplitude. But now I need to specify like which states I need to substitute. So in this A-type HGQM, we have kind of two types of distinguished states. So given the differential of U1 invariant, differential form on X, so we can construct the following state psi gamma that is constructed in the following way. So we take the kind of first entry to be gamma, and for integer vector, we just set it to 0. So that is our state psi gamma, and this state psi gamma, it obeys some nice property. So if kind of gamma was the closed differential form, then that implies that Q acting on state psi gamma is 0. And for all gammas, we have this property that G plus minus acting on a state, acting on this state psi gamma is 0, and that holds in a trivial way because the vector field is just 0, and substitution of 0 vector field would give us 0 answer. So that is kind of one type of state. So that are states that are labeled by tropical forms. And the tropical forms, they are essentially a limit of observables in a Gromov-Witten theory, which we kind of average over U1 action, U1 to the n action, because this action is compact, so we can kind of perform averaging over it. So that's why this property is satisfied. So now, given the kind of integer vector, so given an element of this n-dimensional lattice, we can construct another type of state that is labeled by this vector, and this state is constructed in the following way. So we have, like in this situation, we have a distinguished vector, which is zero vector that always exists in vector space, and similarly, for differential form, there is always like constant differential form, or we can just choose it constant equal to 1 differential form, and for a vector, we choose this vector b as our second entry. And once again, this state is kind of equally nice because this differential form is a constant form. So if I act by q on this state, I would get 0. And similarly, if I act by g plus minus on this state, I will also get 0 because substitution of a vector field it decreases degree of differential form by 1, and here we already have 0 form, so there is no way to decrease. So therefore these states, they're kind of maximally nice, so they are annihilated. So in a case when gamma is Poincare dual to a cycle, which is usual setting for Gromov-Witten theory, we have like all three differentials annihilating this pair of states, psi gamma and psi. And because both G plus and Q annihilate, so these states they are naturally from a kernel of the mixture. So for us that is not important, but for some physical interpretation, people kind of like to look at some kind of amplitudes or more general correlation function on graphs, or for the states that what they call vacuum states. Vacuum states in physics. While for us it is just kind of side remarks. For kind of physics-oriented audience, but for us, these properties that we will use later. Okay, so now we at least defined all objects in the right-hand side of our theorem. So we defined this integral of a moduli space kind of earlier. Okay, so we have kind of summation of the different types of tropical curves. So to be more kind of pedantic. Okay, so now we need to kind of understand and kind of sketch a proof for this theorem 1. And for that, unfortunately, I need to erase something. Yeah, let me erase this part. So this part is we are not going to use. We are only going to use it in the next lecture. So I can easily. Okay, or we will use it later today, so I can erase it. But I just want to keep like all definitions on a board, and then we will gradually replace it with stuff. So okay, so now let us kind of okay, and let us also recall from last time that K that stands in this definition of amplitudes was a Q homotopy, but not arbitrary Q homotopy, but kind of very special Q homotopy given by an integral formula e to the minus t Hamiltonian, and here G plus. Okay, so now let us kind of look at this expression. Okay, so first of all, we recall that correlation function itself is kind of a sum over different graphs, weighted with 1 over automorphism of a graph, and here we have summation over different permutations of some symmetry group, that is symmetric group of whatever number of arguments here we have, like little n plus plus all this number of insertions of the states associated to compactifying hyperplanes. But the object that we have in the end is an amplitude with this psi gamma states and psi b states. Okay, so in kind of tropical Gromov-Fit invariant, we also have summation over graphs, and we have some moduli space integral. So it's kind of not hard to believe that probably summation over graphs here and then summation over graphs here, they are the same type of summation. So therefore, let us kind of focus our attention on kind of relating a kind of an amplitude A gamma with a fixed gamma with an integral over moduli space of kind of fixed tropical curve with fixed decorations, and here some product of evaluation maps for this observable gamma. Let me omit tropical. All our gammas will be tropical from now on. Okay, so therefore here we can kind of ignore that part and first focus on proving why a single contribution, which is integral over moduli space of fixed gamma, equals to amplitude of A gamma with some insertions. So in this moduli space we also remember the degree of the curve, and kind of degree of the curve is encoded in a number and type of this type B insertion. So kind of let me start with different colors. Let me color this a little bit so we have psi gamma. We have here kind of tropical curve in toric variety X with a curve type beta, and this data kind of encoded here, and let's see, last bit is the choice of gamma. Okay, so yeah, so now let us check. Okay, so let us kind of start looking at this amplitude. Yeah, okay, so let us look at some kind of subtree inside of LH tree. So let me start looking. So my tree gamma has this schematic form. So we have some state psi gamma k, and another state psi b. Psi ba. So then they kind of meet at a vertex where they multiply using mu, and then we act with this kind of kg minus on this thing, and that gives us a state that is used as an input for this remaining part of the amplitude. So let me first focus on this subtree. So we can explicitly write down this state. So it's kg minus mu of psi gamma k and psi e. And let us even do the following thing. So let me. So remember, we have this symmetry that allowed us to kind of move around this special vertex where we have mu3 0. So let us kind of rearrange our amplitude in such a way that mu3 0 vertex is just kind of next to this multiplication vertex field. And in this trivalent vertex, so there are like some other two subtrees that kind of connect to it. Here we have this. So therefore, schematically, this amplitude looks like mu3 0, and here we have a kind of this contribution from this subtree where we multiply two states first, then act with kg minus, and let me call these two vectors like v1 and v2, and then some other vectors produced by kind of evaluating this subtree. So that is kind of our amplitude. Okay, so now let us use explicit form. So now we have a very explicit HTQM, and try to simplify this expression. So this expression and kind of mu3 0. So now I think to erase that one. Because we kind of partially have it here in schematic form. The correlation function is essentially sum of amplitudes. So, okay, so let us once again just look at this expression kg minus mu psi gamma. Let me kind of just call it psi gamma and psi b, just to avoid being overcrowded with indices. Okay, so what is the state psi gamma? So state psi gamma. Okay, let's read from right to left. State psi b is 1, comma 2. So that is our state psi b, and then we have a state psi gamma, which is gamma, comma 0, and we need to use mu to multiply these two states. And kind of result of this multiplication is state gamma, comma b. So gamma multiplied by 1 is gamma, and 0 plus b is. So now we need to apply kg minus to this state. So let us recall this formula for k. So let us keep g minus. Now we have g plus from our definition of k. And we have integral from 0 to infinity dt e to the minus th. Okay, and now let us kind of continue rewriting it. So let us recall what are these operators mu g plus g minus. So and act on this thing. So what we would get. So once again, e to the minus th commutes with all this g plus g minus, so we can write them in arbitrary order. Okay, so here e to the minus t, and here Lie derivative with respect to radial vector field with components in standard basis equal to this vector b. And here is a substitution of a two vector field. So we need to substitute radial vector field, and we need to substitute kind of angular vector field, and both are constructed from this vector b, substitute into gamma, and vector b is kind of unchanged. So here we kind of gradually evaluated this state. Okay, so now let us do the following trick. So once again, all our kind of so these phi's, they are all angular variables. So let me add kind of add a trivial integral over this little curvy phi variable. So this is just equal to 1. So it's d over d phi integrated from 0 to a 2 pi, and v divided by 2 pi. Okay, so now let us kind of evaluate this expression. Okay, so let us just focus on Lie derivative. So let us recall definition of Lie derivative. So if you have vector field V, then for a vector field V, we can construct a kind of flow along this vector field V. So and so this flow is some solution to equation gamma dot equals V. So that would be integral curve, and then given an integral curve, we can define a diffeomorphism that takes us from t equals 0 of integral curve. This integral curve will be like gamma of x naught and at time t. So it takes kind of input position of a point at t equals 0. Gamma of 0. And then it kind of gives us a family of points in x parameterized by a time t, which is just a flow of this point x0 along vector field. So then we can use this expression. So this gamma at a fixed moment time t is also point in x. So therefore we can treat this gamma of x0 t as a family of maps x to x. So it takes point x0 and maps to kind of value of this integral curve at a time t. So furthermore, we can show that these maps, they are actually diffeomorphisms because the kind of inverse of it is the same as kind of evolving backwards in time. Okay, so at least for sufficiently small t, all these objects are well defined. So then, depending on the vector field V, these curves like may or may not exist for some infinite time, but we don't care. Here we are looking at kind of small enough t. Small enough. Okay, and then given these diffeomorphisms, we define a Lie derivative acting on differential form omega in the following way. So given a diffeomorphism, we can use it to pull back a differential form. So we will get like this action of this differential form, and we can compare these pulled back differential forms, like differential form pulled back along the flow with original differential form, and kind of divide by t and take a limit t goes to b. So essentially, Lie derivative acting on differential form is kind of describes a change of a differential, infinitesimal change of a differential form along the flow of some vectors. So we can rewrite this formula in the following way. That kind of omega plus some small t LV omega equal to phi t omega star. Okay, so here we got this expression for kind of infinitesimal small t. But now we can treat this part one like omega plus t LV omega as an expansion of an operator e to the t LV acting on omega. And it turns out that kind of careful analysis, like by analyzing a differential equation in T, you can show that that this formula is actually exact formula, not just kind of approximation in linear order in T. That action of e to the t Lie derivative on omega is the same as a pulling back omega along the flow of a vector field for a time t. Okay, let me erase that part. Okay, so let us. So that was kind of some brief recall of some standards from differential geometry and definition of Lie derivative. So now let us use this information to kind of evaluate the objects that we have e to the minus p radial vector field in v direction acting on some differential form gamma. So as we said from our recall, so this thing should be a flow of vector field, and because here we have minus t, so let's say that it is flow for a time minus t along this radial vector field acting on gamma. So now let us kind of make things more concrete and choose kind of standard basis for gamma. So in kind of standard basis of one forms, which is like just gr d phi, so we can treat gamma that is U1 invariant as a function of three types of variables. So it depends on radial variables and it depends on two types of differentials, dr and d phi. So it is independent on phi because we demanded that our differential forms, they are 1 to the n invariant. And kind of action of Lie derivative in angular part would just shift phi dependence by some constant, and the only way to be invariant is to have no phi dependence. So now let us, in this basis, write down explicitly the section of pool. So first of all, RD is kind of constant vector field. So therefore, integral curve from some point R0 over time t for this radial vector field is actually very easy. So it's just R0. Okay, R0 is some n-dimensional vector, and here we just add b times t. So that is kind of solution for this integral curve because the kind of the right hand side is very easy constant vector field. So you can kind of check that it satisfies this Cauchy problem that okay, at a moment of time 0 it is R0, and if I differentiate with respect to time, I will get a vector field whose components exactly equal to v.
So you had too many gammas.
Too many.
Gamma. This gamma represent.
Okay. You are right. Let me temporarily call it omega. Okay. Yeah, you are correct. Let me temporarily call it omega. So yeah, okay. So in this board we evaluate like kg minus acting on mu of psi omega and b. So we will return to gamma only after we finish omega. Yeah. Okay, and then kind of how do we evaluate pullback? So to evaluate pullback, we do the following thing. So for kind of radial dependence, we substitute a kind of an integral curve of a vector field, so R0 plus bt. And now interesting part. So when we act with dr, so acting t on these variables will only act by d on R0, because here t is treated as a parameter. So there is no such thing as dt. Okay, so therefore action of exponent of Lie derivative essentially shift this radial argument of our differential form, replaces it with R naught plus BT. Okay, R naught plus BT. Or okay, sorry, R naught minus BT because we evolve with the time minus. Okay, so that was kind of looking into this part of the operator, but we also have this substitution of a vector fields, and to give them kind of nice interpretation in terms of a moduli space integral. So let us combine the substitution of an angular vector field with this auxiliary integral. So let us look at operator that is defined substitution of this angular vector field once again into differential form, and we will do it in this basis. So what would happen? So this substitution of angular vector field, it kind of removes one of the defis. And kind of replaces it by a component of vector b. But because we also multiply by this d little phi, so we can rewrite it in the following way. So we can rewrite it like this. And here d of capital phi plus b times little phi. And here we need to take a look at kind of degree okay, one form on S1. So here what we do, we just kind of formally shift our angular variables phi by b times calligraphic phi and substitute it into differentials, and we look at kind of one form like a component that is proportional to d phi. And it's kind of not hard to see that is precisely a kind of application of this vector field substitution multiplied by d phi. So when we just have one phi, that is obvious, because when we have one phi, like that our omega is some, say, function f multiplied by dr d phi. So then this operator, okay, we just have one b. So what it does, okay, up to some sign, which I'm now very careful. So what it does, it kind of replaces d phi by b, and kind of multiplied by d phi, and you can check that the sign that we got by commuting d phi to the front place will be cancelled when we commute back d phi into place of this d capital sign. That will be exactly dr d curve. So and as you can see, the action of exponent of any derivative, it sort of shifts the first argument of differential form. So it shifts the radial dependence. While the action of this operator, substitution of a vector field in a b direction d phi, so what it does, it kind of shifts another argument in a differential form. And therefore, it's not surprising that if we combine this dt with this thing, yes.
Here in this example, there is no d capital phi in the result.
In the result, yes.
But,
Because we only have like one capital phi originally. But if you have two capital phis, like say d phi 1, d phi 2, so then at the end of the day, we will have something like d phi 1, d2, d phi, plus d1, d phi, d phi 2. So this procedure will replace one d phi into d curly phi.
in the general expression, there is a d phi capital plus b phi small phi. So
Yes.
what's the meaning of this expression? I mean,
It's just a kind of a form on a bigger space. So this expression we treat it now as a differential form on x times some auxiliary s1.
so can I naively understand it as d phi plus b d phi, d capital phi plus?
Yes. So on this space where we have x, whose like sum of the coordinates of x is this capital phi, and an additional s1 with a coordinate phi, so s1 with a coordinate phi. So then the differential forms on this space are differential forms on x tended to this differential form on this s1. And therefore we can kind of pick up a component which is one form along this S1 phi direction, and that would be a result of application of this differential.
I'm still confused here. D capital phi also must be in the result, right? Because here in general expression, if we naively understand it as d capital phi plus b d small phi, then this d capital phi is also in the final results.
No, but here you see restricted to one form from S1.
Restricted.
So that's why I say that yes, it is true that there will be like a component with all d capital phis, but we pick up a component which is restricted to S1.
And yeah, by the way, there is an omega sign before this.
Yes, you're correct. So that is omega. And kind of this restriction is sort of not something artificial, but it will naturally come because we have this kind of integral over d phi eventually. So therefore, here, if we want to kind of integrate this result over d phi, then the kind of the contribution from this part that is independent on d curly phi will be not contributing to the integral. So that's why this kind of integrals will take care of a proper restriction to S1, or in the case of a radial thing, in the case of this radial part, so that would be essentially omega r, and here we substitute r plus bt, here d5. And once again, restriction to kind of one forms on dt would be imposed by this dt. So once again, for people familiar with terminology, so here we are doing some kind of push forward. So we can treat this integrals as kind of push forward. Okay, so now let me erase that part and combine our results into simple formula. Yeah, so all this nice stuff. So we were originally evaluating kg minus of state psi omega and state psi b. And what we got the following thing. So we got a double integral over d phi and dt. So one is from 0 to infinity, and another over circle with some numerical factor. 1 over 2 pi. And here we got the following expression. Let me continue using this notation. So that would be like our omega. And for arguments of this omega, we do the following operation. So we shift r by bt. So that is done by this yellow operator, exponential of e to the t. So then we shift dr part also by bdt, to dr shift by bdt, or r inside of this d to be shifted by dt, because and that is this action of this, sorry, orange operator. And here, sorry, so to be more careful, so we just integrate over this space. Let me increase it. So this space is r plus cross s1, and this s1 has coordinate little phi, and r plus has coordinate t. So we want to integrate some differential form that is also formed on this space through this kind of little t dependence. And similarly here, finally, we will have shift of phi by once again d little phi. And to finish formula, we have vector b. And this one is kind of action of the red.
The yellow part should be R minus.
Yes, you are correct. Minus. Okay, so let me kind of, okay, I wasn't careful with the sign. Let me put a minus sign here and kind of put minus here as well. So because I want this shift in R to match in kind of yellow and orange mode. Okay, so that is kind of a result of evaluating some subtree. So now let us give interpretation to this result. So when we looked at this subtree, so this subtree, it kind of carried one moduli because this subtree had one internal edge. So that was internal edge. And the moduli space of a tropical curve, it contains, like for each internal edge, the kind of moduli space. So moduli space of this gamma is kind of moduli space of gamma subtracted this subtree. Okay, let me give the notation. Let me call this subtree gamma check. So it's a moduli space of gamma without this subtree gamma check. Multiplied by what? Multiplied by kind of one copy of length and twist. So it is multiplied by a plus times S1. So that's our kind of moduli that we assign to each internal edge. And our subtree, it kind of took away one internal edge from our original graph gamma. Okay, and now we basically see that here we are integrating precisely over this additional moduli or over moduli carried by this subtree. So that is moduli of subtree. Okay, and now when we integrate over moduli, so we need to integrate something over moduli. So now and here, why we kind of made this additional assumption that orange vertex is kind of our okay. So we need to make one additional step. So this is the moduli, and now I need to make additional step, so I need to make some manipulations to this subtree. So let us once again make, I can do manipulations on this one. So we have this subtree, and let me kind of reinterpret the subtree in the following way. So we have this internal edge, and we usually depict internal edges by red. We have this kind of special vertex, and we have this kind of leaf labeled by this integer vector b. And kind of let me reinterpret this psi gamma by just giving it slightly different notation. So it is still kind of psi gamma, and now let us look kind of how this psi gamma act. So this expression kg minus, okay, so this formal expression kg minus of mu psi omega psi b, I can actually reinterpret and write in the following way. It's kg minus O omega acting on state psi b for O omega being operator that act on a state, okay, too many omega, chi m, and it acts in a simple way. It just multiplies omega to the left on this state chi and keeps them. So that is kind of definition of my operator O omega. So it's just operator of multiplying by differential form omega. So therefore I can reinterpret, like from a point of view of amplitude in HDQM, there is no different for kind of amplitude on this subtree where we treat psi gamma and psi b as two external states, and an amplitude of this type. So here we have operator O omega, and here kind of state psi b. So and kind of so these two kind of subtrees, they have identical amplitudes. That if I trade kind of a leaf with psi omega assignment to a two-valent vertex with O omega assignment, so the amplitude, the value for the amplitude literally remains the same. So this phenomena is known as the state operator correspondence. So we mapped like some state psi omega into an operator O omega. So this state operator correspondence is kind of a certain special property of quantum mechanics on trees, because without trees we can't play this trick, because if we don't have this kind of multiplication vertices mu, then we can't kind of trade operator to states. However, it is not property of all states. So I can just take okay. So I can take any state into an operator by just formally define O for a state psi as operator multiplication by a state psi. However, not all linear operators could be written in this form. So this state operator, like going from state to operator, is always possible, and kind of interpreting action of some operator as a state, that is not always possible. And kind of in original setting for Gromov-Fitz invariance, so this kind of observables, okay, gamma or omega, so they have this natural role as an operators inserted in some marked points. And the fact that we managed to kind of reinterpret them in terms of states is kind of very special property of this operator. That if it was some other operators, then we might not have this property. Okay, so therefore, on a level of amplitude on a subtree, we can kind of easily go from this original subtree where we computed it to a subtree that is kind of looking kind of more tropical Gromophyton theory friendly, which is subtree with a leaf labeled by B and some two-valent vertex with omega insertion. So now let us recall that if we have this kind of subtree in a tropical setting, and this vertex is our kind of the vertex, the special vertex or center of mass vertex. So and we have like some other contributions. So let us schematically write down the full expression for modular space integral and try to kind of get decompose it into subtree and other contributions. So the full integral over this modular space of gamma with x beta, and here we have a product of these tropical evaluation maps of all these various observables. Let me still keep calling them omega alpha and we have like some number of these observables. So this modular space was essentially a product of the following type. So we had like a center of mass position, like r to the power n, and n copies of S1. So in this modular space, the coordinates were like the center of mass coordinate RC and phi c times some number of copies of R plus and S1, and the number of copies was one copy for each internal H of gamma. So now if we have our gamma in this schematic form with some kind of subgraphs, I don't know, gamma 1 and gamma 2, and this other subgraph that we analyzing, and because we choose our center of mass vertex to be like the kind of junction of these three subgraphs, so I can schematically write down it in the following way. So there will be like some part where we integrate over R plus cross S1 for each internal H of gamma 1. So that would be, so the center of mass is here, so it is not present in gamma 1, so the only moduli left in gamma 1 will be moduli for internal edges of gamma 1. And here will be some observables on gamma 1, let me call it N1, and similarly, there will be some observables on gamma 2, and we have like the same story for gamma 2. And what we have, and then there will be an additional contribution, which is contribution for a single internal H of our kind of third subgraph that we analyzing. And here should be, okay, so we only have a single observable in this subgraph, so that would be the single pullback evaluation map at our single marked point applied to our form omega. And then there will be overall integral over the center of mass position. So center of mass position, and here we kind of take an integrals over some subspaces or subspaces of the model space. Okay. So now let us recall for evaluate a pullback of evaluation map acting on omega, and once again we evaluate it in our notations when we treat omega as a function of r, dr, and d5. Okay, so let us recall what is evaluation. So evaluation essentially evaluate image of this mark point. Because we choose orange vertex to be our center of mass vertex, so to kind of to get from this orange vertex to our marked point vertex, we need to go kind of along this red edge, and we need to go in a direction opposite from an arrow direction on this. So therefore, evaluation map basically takes takes the data RC by C, and for each red edge we have assigned length and width, and then there will be like a lot of data assigned to these other edges on gamma 1 and gamma 2. So that is kind of gamma 1, gamma 2 modeling. So however, for evaluation map here, because our center of mass vertex is kind of just nearby our subtree, so its value would be independent on this additional moduli. So that's why I'm not even giving them a name. And the answer would be the following. So because we going against this red arrow, so we need to kind of put an additional minus sign when we're moving along it, and we're moving along it for a time t. And in this B state psi B is kind of assigned this integer vector B to this edge, and here because of kind of conservation of or vertex balance condition, so this vector would also be vector B. So therefore, evaluation map returns us in a radial direction RC minus BT, and in an angular direction phi C minus B flat. So that is explicit evaluation of this evaluation map in our setting, and therefore it's not hard to evaluate pullback for this evaluation map. So what we need to do, we need to substitute, like instead of R, the R component of evaluation map dt, and the same for dr, rc minus dt. And similarly for angular part, phi c minus d phi. And so that's what we get by evaluating pullback of evaluation map applied to observable omega in kind of our text. But now if we compare this expression with this expression, so they become identical if we kind of identify R with RC and phi with phi C. And now we can additionally recall that what we evaluated here was only kind of part of the amplitude. The full amplitude, it is written here, was a mu30 pairing of these three states: state V1, state V2, and this state. So now we can call state V1 is some kind of amplitude evaluated at this gamma 1, V2 amplitude to sub 3 gamma 2, and kind of mu30 part of this V1 of V1, V2, and our state is nothing but kind of integral over x of our state, of our omega with all these arguments shifted. And here we will get like some other vectors v1 and v2 that we obtain it from. And these vectors will also have their own omega 1 and omega 2. But what I want to point out that here we have integral over x, and this integral over x is kind of the same as an integral over Rn cross S1 to the power n, because that's essentially just the center of mass position for this tropical curve, and this tropical curve is somewhere inside x. So therefore, if we compare like this final expression for amplitude using explicit form of μ30, we get that it resembles. Let me different color. So we have this omega 1 and omega 2. So omega 1 would be kind of some contribution like this from one subtree, and omega 2 here would be a contribution from another subtree, and this integral of x would be kind of overall integral over this moduli of the center of mass point, and for this last omega here, we saw that this omega that we computed using kind of HTQM procedure is identical to omega computed using pullback of revelation. And once again, we can kind of iterate this procedure and kind of get a full proof that not only this kind of subtree, not only this in this setting we get a matching where we choose somewhat, okay, the subtree is generic, but we choose somewhat special position for a center of mass vertex. So to prove a kind of generic statement, we will need some additional properties of this map, okay, which I erased. Yeah, okay. Of this. Yeah, we will need some additional property of this pullback map along the vector field. So in particular, like if we apply this pullback map to a product of two objects, that is the same as taking a product of two pullbacks. And that's what allows us to essentially kind of propagate this procedure further into our tree gum. So if we have just example, yeah, okay, I can. So if we have a kind of more complicated situation, say we have like center of mass vertex, and we have some kind of story like this. So we have this internal edge and this internal edge, and say we have two observables like marked point 1 and marked point 2 here. So then we already know how to kind of handle this situation. So we know how to evaluate this state corresponding to this situation, and for this state we would essentially have so if here we assign omega 1, so this state that is kind of incoming to this vertex will be essentially a kind of evaluation map of omega 1 and some bits. So evaluation map of omega 1 kind of relative to this one. So now if we have some other observable and we move this thing, so we will apply some, okay, additional moduli T1 and T2. They will be like T1, L, radial part, and another radial part. Apply it to some expression like this, and kind of applying this additional sort of pullbacks with respect to vector field flow will just give us a kind of evaluation. Will just give us a kind of a longer flow, which will include like three pieces. So first flow from one to this vertex, then flow from this vertex to mark point 2, and then flow from mark point 2 to center of mass. So so it's kind of okay. So it takes a bit of time to justify for yourself that that the result would be eventually kind of evaluation map for observable omega 1. Okay, there will be something other evaluation map 2 for observable omega 2. There, here some kind of detail. Here we will have some additional edge. So that kind of so we've proven this statement in some very special setting, but this setting can be generalized to arbitrary tree, and kind of arbitrary tree we can eventually turn this quantum mechanical expression using this geometric interpretation for e to the t Hamiltonian and g plus dt g minus d phi, turn them into this geometric expression that the application of these operators is nothing but applying kind of pullback with respect to evaluation map along the path from some center of mass vertex to each of our observables. And this kind of final pairing in quantum mechanics is the same as kind of integrating over the center of mass position, which serves as kind of starting point for all these passes to various observables.
Yes. Actually, we're comparing the we call it A-type amplitude using brackets to define, and the
moduli space
integral.
Yes.
But yeah, in moduli space integral, it's clear that there is a x integral, which is something like center integral. But
yeah.
In the definition of A-type amplitude, where is this?
In definition of G, like remember, mu30 was a composition of G and mu.
Yeah.
And G itself on kind of omega 1 m1, yeah, omega 2 m2 was kind of, so if m1 plus m2 is 0, which is kind of standard vertex balance condition for this three-valent vertex with all arrows incoming, here with precisely omega 1 h omega 2 integrated away. So pairing in quantum mechanics plays a role of this overall kind of center of mass position integral, and then propagators in quantum mechanics, because for these amplitudes on a G, we insert propagator for each internal edge.
Yes.
Then reinterpreting propagator, like reinterpreting kg minus propagator as kind of integral over to phi t with some artificial factor 1 over 2 pi e to the minus th g plus g minus. So we explicitly evaluated this expression and observed that this is nothing but kind of piece of evaluation map. So when we kind of evaluate our observable relative to some point, to some endpoint, and then because this kind of evaluation maps acting on a product is sort of product of evaluation maps, then having kind of more observables along the way would still give us kind of full evaluation map for a fieldless observable. So kind of this bit of relation map would kind of be responsible for this kind of bit of motion along the path from center to mark point 1. So this e to the t1 L are what kind of sort of be a piece of pullback correlation map for both observable 1 and observable 2 because of this multiplicativity property. The omega 1 by omega 2 general pullback map. This kind of pullback map of omega 1, wedge pullback map of omega 2. So therefore, like this piece, because here as an input we will have some product of something concept from omega 1 and omega 2, but when we apply this final kind of pullback, like pullback from this expression, we can kind of individually apply it to omega 1 and omega 2. So for omega 2 is just the end of the story. It just gives us kind of proper evaluation map for this setting. But for omega 1, that would be like one of the edges for computing this evaluation map. The evaluation map was kind of sum from contributions from each of the internal edge that we traverse moving from center of mass to an observer.
Inside this tree, there is a main road connecting center and any.
Yeah, so that is a property of a tree that you can always choose uniquely a kind of path between two pair of vertices. So treating observables as a two valent vertices, so then it falls to this theorem. So there is unique path between any pair of vertices. So we fix one vertex to be the center of mass, and then we have like unique passes to all marked points.
It's like an auxiliary selection, which paths which we choose to be the main road.
No, there is kind of no choice. Okay, maybe I'm not sure. Yeah. Yeah, maybe something like this. So add two more observables, let's say 3, and observable 4. So in such a way that kind of passes to observable 3 and observable 4, they are two different paths. But because here we will have like multiplication of these two objects, so we will have like mu, and here will be some kind of partial evaluation map 4, and partial evaluation map 3 applied to omega 4 and omega 3. So each of them is constructed from their own passes. But then kind of here these two passes merge, and therefore here when I apply like kg minus on this edge, I just kind of continue traveling, like continue pulling these two observables towards the center of mass. And then because here when I apply something like a pullback, that will be equal to a mu with a pullback applied to kind of each. So and I can now represent it as kind of traveling along this path for observable 4 and kind of traveling along this path for observable 3. So we don't need to have like a single path that will traverse all observables, because of this property we can kind of split action of this piece into both paths. But as I said, that was kind of one of the so this theorem 1 was kind of rather non-trivial theorem in kind of in this tropical mirror symmetry, because it took us quite some time to kind of carefully analyze all the settings and give a careful proof. So that's why, yeah, please not be surprised that in a span of like hour and a half, you kind of can't quite get all details. So that is kind of some technically complicated part of our construction. Because here we need to kind of carefully analyze like what happens in this situation, what are these subtree, how the evaluation maps interact with various bits of quantum mechanics, that kind of adding additional kg minus is like modifying evaluation maps by shifting the center of mass vertex along one edge. So the proof was kind of long and tedious proof of carefully analyzed things. But essence is kind of, I hope the essence is clear that this evaluation maps, they kind of originate from exponents of Lie derivatives, but we need an additional G plus G minus, because exponent of Lie derivative would treat these parameters T as just fixed parameters, so they wouldn't enter into differential, and to kind of get a form on the moduli space, we need this G plus G minus, and that is sort of the same story as in 2 dimensions. That to get kind of form on the moduli space, we need to get this G plus G minus assumptions. And just as a side remark, so this proof is kind of the way to prove that some formal expression in, say, Morse theory, where we typically have some k with the exponential form, that it also can be repackaged as some kind of moduli space integral and later interpreted as some enumerative problem. So the method is kind of the same, that we need to kind of carefully reinterpret e to the kh and kind of g plus part, g plus dt part, as a kind of two bits of a single pullback of some evaluation map, and then we need to kind of repeat this procedure till we reach some kind of special point where we perform pairing quantum mechanics, or some special points which we choose when we describe the moduli space as a closure.
Yeah, but here the LR, the Hamiltonian, depend on the state, that's the B depend on the event.
But because we were given in a graph, because B can change, like so that's why we need to keep this dependent, because like here we will have some B1, B2, and the kind of vector assigned here would be B1 plus B2. So that's why when we evaluate this e to the th on different edges, we need to keep track of kind of what vector is assigned to this edge. And the way to keep track of it is kind of assign some states, but in a Morse theory there is no kind of branching. So essentially like this analog of this vector b, it stays the same. So that's why you don't see it anywhere in computation, because it's just a flow for the same vector field. And here we have like evaluation maps with respect to different integer vectors assigned. So that's why in quantum mechanics we need to keep track of this information with integer vector assignment.
Yeah, so that's the reason why we consider in toric target. And we can remember all the velocity, you can call it velocity vector. Those B's will remember the direction of propagator.
So I think that like many things that requires toric things. So yeah. So starting from kind of data about our complex manifold, because for a general complex manifold the data is not a simple combinatorial data. So that is the property of a toric. So then we also have the special splitting of our coordinates into radial and angular coordinates, and all this idea of averaging over angular coordinates, that kind of requires some compact group action on our variety. So that is another reason why we need toric variety to have like all this U1 action magic and kind of adding and removing these integrals over d curly phi, because essentially quantum mechanics is kind of operates in sort of one-dimensional source space, and our source space is essentially some kind of local time variables assigned to this graph, and to ignore the angular part, we need to have an ability of like averaging stuff and kind of like angular part somewhat to be compatible with radial part. So notice that these b vectors, they're kind of universally assigned. So the evolution in angular direction and evolution in radial direction is kind of controlled by the same integer vector. So we're not assigning like pair of integer vectors, one for angular part, one for radial part, and the partial reason for that is that the kind of toric variety kind of fixes these evolutions to be identical. So that's why there is kind of there is no like single reason why we need toric variety. That kind of toric variety sort of simplifies so many things in the quantum mechanics. So that's why like if you ask me like which part would fail if it's not toric, I would say like the full construction would fail if it's not toric. So
yeah, but the same construction remind me something like Morse tree. Like each edge is like a gradient flow for some.
Yeah. So somewhat yes, it looks similar to Morse tree where you assign like collection of some Morse function for different edges. But I don't know. I haven't like studied in details this Morse tree business, so I can't say like how much of this analogy is useful. Okay, I think we should definitely make a break. Way overdue for a break. I apologize for that. Let's take a 10-minute break from 11:41 to 11:51. And then we will discuss theorem 2. So theorem 2 is kind of easier than this one, because here we really need to use a lot of differential geometry to do it. But theorem 2, I can at least explain the kind of the rough picture of it in pictures. So that will save us something. Okay, I'll be back. Okay, so our focus is area 2. Okay, so theorem 1 kind of allowed us to turn this object, which was tropical Gromov-Fit invariant, some enumerative thing or moduli space integral thing, into amplitude, into correlation function, which is some weighted sum of amplitudes in a certain special higher topological quantum mechanics constructed from differential forms and some natural operations like Gram differential, vector field substitutions, integral Poincare pairing on differential forms, and wedge product. Okay, so let us kind of look at schematically and this thing. So we have like psi gammas and some collection of psi b's. And this psi b's, their number is kind of fixed by first class of our curve. So all this and k depends on. So now what we do, we multiply this Gromov-Fit, this tropical Gromov-Fit invariant for a fixed degree by q to the power beta and sum over beta over all possible curve classes. So to get some generating function for Gromov-Fit invariance for a fixed observables, but all kind of possible curve classes that can support this observable. So in a Tori case, that is a bit redundant because like given collection of observables, you can usually uniquely determine like which curve class would give us non-zero answer. So this thing is essentially like summation of a beta is like a single term which gives you a contribution and the rest of the terms are zero. But nevertheless, this construction is still used. So here a kind of q to the beta, it has this interpretation, it's kind of q1 to the power n1 beta, so on, q b to the power n b. So we just product of kind of bunch of q's raised to this integer powers. So equivalently, we can kind of trade these integer powers by kind of saying that because we have like a q1 factor for exactly one q1 factor for each kind of psi b1, so we can just kind of put q1 in front of psi b1 and do the same for all psi's to rewrite the very same thing in the following form. So we still have summation over curve classes, but now here we still have like collection of psi's. But now for kind of psi b's, we just multiply each psi b by the corresponding q. Psi b q. Okay, so far nothing fancy. So we just kind of absorb this standard kind of factor that keep tracks of different betas, absorb it into kind of redefinition of our states psi b by multiplying them by a certain number, or by some formal variables. So now let us recall the following thing. So let us recall that we can obtain all what we call trivalent trees 3 valent trees with n plus 1 leaves by attaching one leaf to a trivalent tree with n leaves. So the idea is kind of rather trivial. That suppose you have a tree with 4 leaves, or let me start even with a simpler example that that if I start with a tree, 3 valent tree with 3 leaves, that is the simplest tree which we can get. Simplest, not yet simplest tree. So then what we can do? So this tree has kind of exactly 3 edges. All of them are kind of semi-infinite edges. So what we can do? We can just attach an additional leaf to each of the edge, and what we will obtain in such a way, we will obtain all 4 valent trees. Yes, and okay. In this case, like all 4 valent trees, so there is only a single type of 4 valent trees. So all these 3 situations will be equivalent, but nevertheless, they will like literally give us all possible 3 valent trees. So in kind of less trivial situation is say a situation when we have a tree with 5 leaves. So we know that there are like 2 inequivalent trees with 6 leaves, and these 2 inequivalent trees are kind of obtained by different choice of leaves. So if we choose a leaf to be here, that would be one type of 3 valent tree with 6 leaves. And if you choose a leaf, say somewhere here, we would get another. Okay, so now let us kind of use this knowledge. So far, this knowledge, if we are not talking about like some multiplicity factors, which will be important because we summing up diagrams with some weights. So the multiplicity factors in this relation would be kind of rather complicated. But modular this multiplicity factors, this statement is kind of rather simple. That getting more leaves means attaching a leaf somewhere in a tree with 1 leaf length. So therefore, in kind of our sum, let us try to do the following thing. So we have kind of 2 types of states. So we have state psi gamma, and we have state psi b. And the theorem 2 basically tells us that there is a way to kind of perform this summation that only states psi gamma survive. So therefore, let us, if we have like this state psi gamma n of them, so let us start with a tree with n leaves, and we assign some psi gammas to this leaf. Gamma 1, psi gamma 2, psi gamma 3, and so on, psi gamma n. And then we can kind of to get a tree with a higher number of leaves, we can iterate this procedure. So we start with assignment of some kind of red leaf, let me call it additional leaf 1, or we can assign some leaf 2 in some other place, and so on. So we will assign this red leaves till we reach the required number of leaves by theorem 1. So the number of red leaves equals to this total number of k of b, the total number of this psi b insertion that we need. So even though it sounds like a good plan, but there is like one obvious issue, and kind of obvious issue is that no, okay. So at this stage there is no obvious issue, so we can just get it. But let me kind of draw a picture like this: that attachment of next leaf, like say leaf 4, it can be attached to a new edge created by a previous leaf. So therefore we will have like kind of two types of picture. That it's like a simple red leaf attached somewhere to a white graph, or some kind of red subtree that is also attached to a white graph. So there can be two situations. It's simple red leaf and kind of red subtree. Okay, so let us kind of memorize this case. We will return to it later. But before analyzing these cases, let us do one more simplification. So in this sum of a beta, we have this number of leaves of the different types. It's kind of controlled by a curve class beta, because kind of beta has this many components, and it tells you like how many each compactifying hyperplane is intersected by semi-infinite edges of the curve. So let us kind of observe the following thing, or let us not even observe, let us recall. So let us recall that in quantum mechanical amplitude, as we just discussed on this board, we eventually have some mu3 pairing of some kind of states on some subgraphs. So somewhere in our amplitude, so we have like some three subgraph results of three subgraph evaluation meeting at this special vertex where mu3 turns them into null. So far for this moduli space integral, we kind of used the part that was integral over x of the corresponding omega 1, omega 2, and omega 3 to kind of get a moduli space integral interpretation. But let us recall that proper mu3, it also contains an additional check that m1 plus m2 plus m3 should be equal to 0. So this check was kind of not very interesting in relation to a tropical moduli space integral, because that was just vertex balance condition for this special vertex with three edges, with all three edges are in kind. So that was vertex balance condition. And our tropical curves, they were automatically satisfying this vertex balance condition. So this evaluation was non-zero. So now let us kind of use this additional vertex balance condition as some additional selection rule. So what is the idea? So when we assign these additional leaves, so we assign them together with some integer vector. So we will assign the states psi b, and now let us see what happens to this integer vector. So remember that in the multiplication, we take a wedge product of differential forms, but we also add up this integer vector. So there and in this tree we only have three valent vertices, and somewhere we have this special, say, okay, I draw it orange vertex. Orange vertex where all edges are incoming. So let me orient all edges incoming. and that all red edges, we also choose them to be incoming. So now we can easily, in this arrangement, we can easily compute integer vectors for each edge. So if we want to compute integer vector for, say, this orange edge, so what we need to do, we need to kind of see which kind of subgraph kind of enters, which subgraph is connected to this edge. So if we cut over this edge, we will get like some subgraph. And for this subgraph, we have like observables omega, gamma type observables. They carry no vector, so they kind of gamma comma 0 state. So 0 vector from here, 0 vector from here. Mu2 take a sum of these 0 vectors, so it's kind of 0, 0, 0. And here we have vector b1. So vector b1 will add it to 0 vector. Therefore, we will have vector b1 running over orange edge. And it's kind of not hard to see that the sum of the vectors of this m1 plus m2 plus m3 in this vertex where we perform kind of integral and we check that the sum is 0 is nothing but the sum over all kind of integer vectors assigned to all red edges. Because all of them just kind of get added up in each cubical vector. So now, if we arrange a number of vectors b alpha to be according to the curve class, so this condition will be automatically satisfied. But now the interesting part that now that if we relax this assumption, just assign an arbitrary integer numbers n1 to nb of vectors b1 to bb. So then we will see that for some assignments, this condition would not be satisfied. But that is not a problem because such amplitude just equal to 0. So there is no problem to include kind of 0 amplitudes in our sum. So it doesn't change sum. And the only way to satisfy this condition is kind of to have like all these b vectors like n alpha, b alpha, summed over different kinds of vectors equal to 0. And this condition is precisely a condition for consistent tropical curve. That kind of number of independent solutions here, number of independent solutions for this integer vectors in alpha is precisely equal to a dimension of a second homology group for X. So that's something that we computed in earlier lectures. That dimension of a second homology group was a number of vectors b minus complex dimension of X. And here, because we have like one vector equation, the sum of some vectors equal to 0. So in components, it will give us exactly capital N equations, and the number of variables is the size of this set of compactifying hyperplanes. So therefore, given that this system is not degenerate, the space of independent solutions would be a vector space whose dimension precisely match with dimension of second homology block, which is same as dimension of space for a different curve class. So therefore we can do yet one more simplification to this sum. So we are kind of continuing writing it. So here we have a summation of a beta, but I can replace it to summation over all independent n1 to nb ranging from 0 to infinity. And here will be psi gamma 1, psi gamma n. And here let me just write like this formal notation. Like 10 to the power means inserted n1 times, and similarly qb psi d inserted n d times. So because of this extra kind of property for pairing for this triple pairing of three states into numbers in quantum mechanics, we can kind of add a lot of zero amplitudes to this sum and replace it by much bigger sum where all these numbers freely run from 0 to infinity. They're not kind of related to each other. Like in this sum, they were all controlled by a single curve class beta. And here we say they are completely independent, and this kind of property of a pairing will ensure that the only non-zero contributions would come from kind of tropical curves. So would come from situations when we have vertex balance conditions satisfied in all vertices. And here we sum over kind of all valid tropical curve classes, and therefore here we will also pick up non-zero contribution from all valid tropical curve classes. So that is kind of a huge simplification for two reasons. So first of all, this summation over all these n's. So unfortunately here I like simplified some symmetry factor. So I think there is some product of n factorials for a symmetry factors. Let me upstairs. So if you take into account properly symmetry factors, so the sum with restored symmetry factors can be further simplified in the following form. So we have only one variable. Okay, little n is bad because we reserved little. Let me call it m. And here psi gamma 1, psi gamma n. And here I will introduce new notation wx, which is kind of preparation for mirror superpotential, but right now that is kind of universal psi b state. So it is defined in the following way. So we take a sum qk psi bk k from 1 to b. So with some proper symmetry factor, like 1 over product of factorials and 1 over n factorial here, so we can replace like insertions of capital B different types of this boundary hyperplane states by insertion of a single kind of universal hyperplane state, because if here we kind of use linearity of this correlation function and just expand in powers of q, we will get precisely this expression that will be like a product over individual n factorials with kind of n1 to nb insertions of each type of the observer. So that essentially allows us to treat this psi b states not as a different states, but as the same type of states. So here I can just erase this label b and kind of imagine that everywhere here I have this universal insertion of this universal kind of hyperplane state. Okay, so that kind of simplified story, because now there is no additional labeling for red leaves. All red leaves are the same. So now let us kind of recall this bit. That there are two possible ways how red leaves can be attached. So it's attached as a simple leaf to kind of somewhere to white edge, or attach it as a red subtree. So there is a simple lemma. Okay, let me keep this board for rewriting. So lemma amplitude with red subtrees vanish. So once again, we can freely add and subtract zero contributions. And here, so first we kind of included all these red subtrees to generate like all possible types and all possible assignments of this red and white observables in this expression. But now using this lemma, we can kind of eliminate contributions when we have insertions of red subtrees, and only count the contributions when red leaves are kind of simple leaves attached to this white tree. And the reason for this is very simple. So let me look at simplest red subtree. So simplest red subtree, it has like all red subtrees, red subtrees. They have like this kind of common thing that it's two red lines joining into another red line. So now let us recall how we compute the amplitude. So there will be like some other part of our tree. And once again, nothing prevents us from choosing this vertex, some other part of some tree, from choosing this orange vertex to be a vertex where 0 is inserted. And that kind of vertex where we will take a product of three states, check, and product of three states, check the sum, whether it is 0, and evaluate integer. So therefore here let us compute what is the value of this state omega b, that is this state that is incoming to this orange vector. So this state is constructed in the following way. So it is kg minus, because we have this red internal edge. Applied to multiplication of two universal kind of universal leaves, like wx and wx. So now let us recall that that kind of wx is a linear combination, some q's, linear combination of this psi b states which have the form. It is 1 for differential form and some vector b assigned for this element of interrelation. So if we multiply two of such states, so what we will get? We will get like some qk ql double sum of the following type of state. So it's still identity for a differential form, and here will be like k plus bl. But remember, when we introduced these states, we noticed that these states, they are annihilated by g minus. So this psi, so this state is essentially psi dk plus bl, and g minus acting on it acts by 0, because differential form is degree 0 form, and there is no way to lower the degree. So therefore the contribution from this subtree, so this kind of red subtree would give us sort of zero differential form as kind of one of the inputs for this multiplication. So therefore this U3 multiplication would just give us 0, because the red subtree provides a zero factor in this multiplication. So that is kind of another simplification that allows us to perform summation, because right now what we get that here the only amplitudes that contribute to this correlation function, they are amplitudes on the trees that are constructed in a very special way. That we take a white tree with n leaves, and then we assign kind of the simple red leaves. So M simple red leaves, and little n kind of white leaves. Okay. And furthermore, summation over n basically tells us that we can kind of attach any number of these simple red leaves. So kind of schematically, for say 3 observables, example for n equals 3, the picture would be like this. So we can like attach no red leaves. So that would be like one. We can attach one red leaf in kind of any kind in any of the 3 locations. So these are kind of three different possible ways of attaching red. So then we can attach 2 red leaves. That will give us whatever 6 something or 12 contributions. Okay, so let me draw some of the contributions. So we can attach like red leaves either on the same white edges or on different white edges. So there will be like many contributions. Okay, so now looking into these trees, we can kind of generate the sum over this kind of white trees decorated by any number of simple red leaves in the following way. So sum over such trees decorated by simple red leaves can be written as the sum over trees with a modified kind of prescription. So for a 3-valent example, so all this sum can be written as a contribution from a single tree with this new type of and in this kind of new trees we have so new trees with n white leaves. So here we have n white leaves and arbitrary number of red decorations on top of them, and we just replace it sum over white trees. But now this kind of okay white trees, okay, some of the yellow trees, but this sum will be summation over trees with exactly n leaves. But kind of each yellow leaf is the formal sum of the following kind. It is just a white leaf decorated once, then a white leaf decorated twice, and so on. So here we can decorate arbitrary number of times with white leaf. And then similarly for this yellow internal edge, we do exactly the same. So it is white internal edge plus white internal edge decorated once, white internal edge decorated twice, and so on, white internal edge decorated arbitrary number of red. And this property kind of requires that all these decorations are simple decorations, because if we allow for red subtrees, then in these sums we would have not just simple decorations, but should allow for arbitrary subtrees, and then it would be unmanageable. So that here will be just sum over. So here was like this arbitrary number of decorations. And we kind of formally replaced white edges with decoration by this kind of yellow edges, which is just formal linear combination of arbitrary decorated white edges. Okay, so now having these trees, okay, so having trees is nice, but now the question is whether we can interpret the sum over white trees as some kind of correlation function in some HTQM. So the question is whether this sum. So previously in HTQM, so this white leaf was corresponding to a state psi gamma, and this white internal edge was corresponding to insertion of some kg minus. So the question is whether this sum over decorated things, whether it gives us some kind of reasonable states and some reasonable propagator in some HTQM. And the answer is yes. And that is kind of verified explicitly. So the simple way, the kind of simply we can start with this kind of psi gamma x, and we can just use the rules of our HTQM amplitudes to just evaluate the sum over subtrees. So it is psi x gamma, so it's psi gamma, and then decorating once means that we so that this edge would be now internal edge. So that would be internal edge with kg minus propagator, and here we would have a vertex where we multiply, okay, wx with universal state on the leaf, multiply with psi gamma, and similarly we can iterate this procedure for a two decoration that will be kg minus mu, and here will be wx with another kg minus of another wx and psi gamma. So all we need to do is evaluate the subtrees. Okay, so we got some state, so it's some linear combination of states. Okay, so this state exists even in original quantum mechanics. So the more interesting part is kind of this deforming propagator. So it is kind of original propagator kg minus plus, and this contribution works in the following way. So propagator is kind of x on some state, so it's kg minus acting on this incoming state. Then we take a mu2 of the result with multiplied by w of x and kind of apply kg minus again. So now, unfortunately, I think at the beginning of this lecture, I kind of, okay, let me put it in this corner. Recall from the beginning of today's lecture, we talked about linearized deformation of HTQM by a state. So, linearized deformation. So that was kind of part of this theorem, how to relate correlation function with n+1 observables to some derivative of correlation function in the formal theory with n observables. So recall that this q epsilon, not q epsilon, let us recall psi epsilon states. So psi epsilon states were constructed in the following way. It was epsilon kg minus psi naught psi. And that is precisely a kind of leading term or attachment of a one leaf deformation of what we are getting in this kind of formal construction of rewriting sum. So the more interesting part is the propagator part. So we have this complicated expression for propagator, while in our construction we had q epsilon, that was q plus epsilon g minus commutator of multiplication by psi naught state. So here, I think it's kind of rather straightforward exercise to see that that if I put kind of little epsilon here, that at the leading order in epsilon, like this kind of kg minus deformed, or yeah, kg minus deformed is actually kind of homotopy multiplied by g minus for deformed q. So that this expression is kind of equal to k epsilon homotopy multiplied by g minus. So k epsilon homotopy would be more complicated, so there will be more terms. But multiplication by g minus to the right would eliminate some of the terms because g minus squares to 0. So that's kind of the trick. Okay, so at least we have kind of immediate interpretation that these two contributions they give us kind of some healthy deformation of HTQM. So that gives us deformation of HTQM that we saw before. So it's HTQM deformation by a state. And here, in this assumption for existence of this deformation, we require two assumptions: that g minus of psi naught is 0 and q of psi naught is also 0. And for our red state, both these properties hold, because red state was a linear combination of this kind of psi p states, and earlier today we observed that psi p states satisfy this property that q and g minus acting on them is 0. So therefore this leading order term with a single attachment of a red leaf, it is indeed a kind of a linearized deformation of some HTQM. So therefore now the new question, so here like
what you use q upside, but use kg minus downwards. So
yeah, but k is kind of q homotopy. So if you deform q, you can correspondingly compute how your homotopy deforms. So roughly picture is kind of like in a very rough terms that k is in a kind of proper sense is like 1 over q, where q is inverted. So now if I have q plus something plus phi, so I can write it as kind of 1 over q plus 1 over q phi 1 over q and so on. So that would be like deformed k will be k plus k phi k plus so on. So now our deformation phi is kind of g minus commutator with the mutual multiplication by something. So therefore here, and if we compute k epsilon g minus, that would be like k g minus, and in the leading term it will be what? K phi k, it will be like g minus commutator with mu multiplication by psi naught, k g minus, and then we will use the property that g minus squares to 0. So here instead of commutator, we would have just k g minus multiplication by psi naught, k g minus.
So q epsilon itself it actually contains a lot of terms, not only linearized terms.
No, so in this q epsilon, we were working in kind of just linear order in epsilon.
But then I think the entire q epsilon will satisfy quadratic relation q epsilon squared to 0, but only the
linear order in epsilon. So it.
But then there will be a second order term.
Yeah. So that's the next question is how to get interpretation of these terms, because so far we only studied linear deformation, and now the question is whether these additional terms can kind of interpreted as a full non-linear deformation in some theory. And it turns out that yeah, the answer is yes. And the reason for that, okay, let me let me erase that part. Okay, maybe I can just try. And the reason for that is the following. So if you take this q epsilon and compute square of it, so the linear order term kind of vanishes because of some q of psi and g minus of psi acting by 0, and the epsilon square term can be written in the following way. As kind of g minus acting on a product of two psi naught states. And kind of, if this thing is 0, so then this q epsilon is kind of differential to all orders in epsilon. And once again, I think I just erased it because this computation was precisely a computation on a red subtree. So therefore, that is kind of first check that this q epsilon is actually a kind of honest differential to all orders in epsilon. So the kind of the non-trivial part is to see that this additional condition is enough to satisfy some other properties of Q. Because Q needs to satisfy some compatibility condition with the pairing, compatibility condition with multiplication, and so on. But it turns out that with this additional property that we deform our HTQM by Q and G minus closed state psi naught with this additional property that G minus on a product of two states is 0. So that allows us to interpret this whole sum as this deformation where we removed word linearized. So kind of to finish this one, so first step that we did was to rewrite this thing as a correlation function. So summation over all kinds of trees with n leaves, it is the same as correlation function. And here we have this state psi constructed, psi x constructed exactly this way. In HTQM whose Q is deformed, so Qx is Q plus G minus commutator with a multiplication by Ws. And that kind of completes a proof of our theorem that we promised to kind of turn this summation of a tropical Gromov-Fit invariance weighted with Q to the power of degree or first class into just a correlation function of just our kind of cycle observables in some deformed HTQM. So kind of just the completeness. So psi x gamma is psi gamma plus 2g minus wx psi gamma plus dot. And furthermore, these states they continue to satisfy some nice property. Like for example, there is like a separate gamma that qx active on psi gamma x is 0. So given that gamma is a closed differential form, so that is Poincare dual to some side. And okay, so for obvious reasons, this thing holds because we deform psi gamma state by something which is G minus exact. So that's why G minus kind of keeps annihilating psi gamma x. And now we have collection of these states which are Q closed and G minus closed. So that kind of naturally leads us to this theorem that I was kind of talking at the beginning of lecture today, and we proved it last time. It was a theorem how we can kind of turn this n-point correlation function into n-1 point correlation function by further deforming this qx by psi nx count. And the thing that we will do next time, we will kind of show that the deformation of qx by psi x gamma n is kind of equivalent in some proper sense, in some cosmologies, to a deformation of superpotential by some holomorphic function constructed from psi n x gamma. And furthermore, this correlation function would be therefore equal to correlation function of some holomorphic functions constructed from this psi n x gammas in Landau-Ginzburg theory with this superpotential Wx. But that will be next time. So for today we just proven these two theorems. So we started with tropical Gromov-Witten invariant. So we managed to rewrite like this geometric construction of a moduli space integral as a correlation function in a certain HTQM. So then we multiplied this simple Gromov-Witten invariance for a fixed curve class by q to the power beta, performed summation of a beta, used the fact that summation of a beta is equivalent to summation over arbitrary number of individual insertions from psi b states because of some kind of mu30 pairing structure that verifies for us that the sum of these integer vectors is indeed 0, which is required for valid tropical curve. And then after taking account some combinatorial factors, we managed to simplify the sum over multiple types of different insertions as a sum with a single universal insertion of this Wx. And then we use this idea that insertions of this Wx can be interpreted as adding some red leaves to a graph, to white graph with n leaves. And furthermore, we observed that the amplitudes, when we add not just a simple leaf but some red subtree, that all such amplitude vanish. So therefore we can just drop them from our sum for this correlation function. And then we observed that the summation over white trees decorated by arbitrary number of red leaves can be interpreted as summation over just yellow trees with n leaves, where we formally replace leaf and an internal edge by this formal sum of arbitrary number of red decorations. And it turned out that this sum makes sense as a deformation of HTQM, and therefore this summation over white trees with n leaves is once again gives us a correlation function in some different HTQM with kind of same vector space, same G plus G minus, same pairing, same multiplication, but deformed Q. So deformation only happens in Q, and this kind of states, they also deform it in some specific. And I think these states, that's what we call mirror state. And kind of this theorem too, sometimes people call it like mirror on the level of HTQM. So and kind of that is something that we are working in two-dimensional version for kind of Gromov-Witten theory and some supersymmetric sigma models. So kind of this AIB mirror by Losif and Frenkel is essentially like two-dimensional analog of theorem 2 that they kind of resum at some amplitudes. So this psi's, they are like holomorphic insertions that resum in an amplitude with arbitrary number of holomorphic insertions kind of became an amplitude in a theory kind of whose supercharge is deformed by this holomorphism and stays deformed in some way. So, and in Losif and Frenkel, they kind of carefully computed the deformation of supercharge, but unfortunately they kind of don't have analog of this formula, how we need to deform states, or how we need to deform like vertex operators corresponding to these gamma insertions in kind of this in this relation, which is their version of theorem.
Excuse me, this is what you call I model, or directly.
I think we don't have like I model in this quantum mechanics. Like I model is just kind of redundantly equal to either A or B model in quantum mechanics. So we don't really need it with any intermediate part, because in two-dimensional case there is some issue about some kind of variables necessary complex conjugated to each other, and kind of going from I model to B model requires some kind of analytic continuation. So fortunately we don't have like all this complicated business in one-dimensional case. So that's why we kind of don't need this I model.
But this yellow is amplitude is not B model right now, right? B model.
No, I think it is B model. So it is not Landau-Ginzburg type of construction, but it is a B model HTQM. So
what do you mean by B model? It's like deformed A model.
Yeah, so it is kind of A model deformed by superpotential. So we kind of get the superpotential. So in a sense, like if we kind of try to take a classical limit of this HTQM, that would be like original HTQM deformed by a superpotential constructed from this kind of compactifying hyperplanes. So that's why, in a sense, it is a B model, and it is kind of Landau-Ginzburg type HTQM. But in our kind of statement for a tropical mirror, right-hand side was not amplitudes or correlation functions in some quantum mechanics, but it was rather some kind of recursive construction for things computed out of holomorphic functions. That instead of just having correlation functions, we have just some simple residue formulas, and there we didn't have like some infinite dimensional moduli spaces and stuff. So everything was kind of very explicit, just holomorphic functions and some operations on holomorphic functions, like no fancy things like propagators or something. So and that will be like content of our next lecture. So we will see how to kind of simplify these amplitudes in a Landau-Ginzburg type quantum mechanics deformed by superpotential. How to kind of localize these amplitudes to some integrals over lower dimensional space of some simple objects, simple holomorphic functions constructed from these states. Because here states, they are like differential forms with some additional labeling by integer vector. So that doesn't look like holomorphic function. That looks like way more complicated than holomorphic function. And next time we will see that apparently there is some additional properties of this amplitude, that dependence on psi gamma x is rather weak, and we can choose like different representative for this psi gamma x in QX cohomologies, and this representative would be precisely a holomorphic function in Landau-Ginzburg type of theory. So that's why there is kind of the step that is not discussed even in Losseff and Frenkel. Like Losseff and Frenkel, they kind of end in theorem 2. So they write like Gromov-Witten invariance through kind of topological string amplitudes, like type A amplitudes, and then they kind of massage it through intermediate model to type B correlation functions, also in some two-dimensional theory. So they never perform like localization of this two-dimensional theory to this recursive construction, to the residue type formulas that we have in Landau-Ginzburg Saito model. So that is a part that was also missing, and the reason why it was missing, because to construct that part, you really need to have like a good understanding of these mirror states, because you want to turn these mirror states into holomorphic functions. So you need a rather explicit description of these states. And unfortunately, in their paper, they have a rather explicit description for this deformation of supercharge to kind of justify that the deformation of theory is done by adding superpotential. But they kind of have almost no discussion to how the states are deformed between two theories, and that is a crucial step to get into this Landau-Ginzburg side of theory, which is essentially generalization of some residue formulas for some holomorphic functions in some like Jacobi ring constructed from mirror superpotential. Yeah, so that's kind of where tropical approach is kind of winning, because of the simplifications in tropical approach, we have a kind of rather explicit form of these mirror states, and kind of by explicitly writing these mirror states, we guessed like how to rewrite them in terms of holomorphic functions and how to connect to residue form. So that's kind of why we think that this knowledge from tropical case could be useful in two-dimensional case, because we kind of expect that the tropical case should emerge as some kind of limit of two-dimensional case. So the phenomena happening in tropical case should have the corresponding phenomena in two-dimensional case, but probably more complicated because of absence of some tropical simplification. Yeah, so that was some kind of extensive remark for some people in the audience who work in two-dimensional case. So, okay, I think we should for sure stop, and yeah, I think I think next lecture is like our very final lecture. Yeah, okay, so I kind of typed half of the homework file, so I think I will just release what I have. So homework 5 will be like shorter than the normal homework, but I think it's still better to have like extra short homework. So, and I will kind of try my best to return graded homeworks by next lecture. So you will have them like graded except the last one, because the last one will be due for next lecture, and so that you will have like your feedback on graded homeworks to prepare for this oral exam that would happen sometime in exam period. It's either normal Tuesday or depending on your schedule, maybe we can do some other day. Yeah, so that is the plan. So there will be, most likely will be homework 5 released today, but unfortunately a short version, like half of the problem. But still, it will be an interesting problem of computing some evaluation maps and some moduli space integrals in some example for a curve in P1 cos P1, just to kind of check your understanding of that construction. So there will be, I think, no exercises in quantum mechanics, because I kind of rushed quantum mechanics quite a bit. So I think it's unfair to kind of ask questions about it in a homework. Okay.
Can I ask you something?
Yeah.
Oh yeah. I mean, here later you will use something like QX homology class to.
Yes, but for that I will need to prove certain things, that this correlation function. Okay, I think we even proven it like 2 lectures ago, that if I have states that are Qx and G minus closed, that they are invariant by shifting by Qx of G minus closed, by Qx xi, as long as xi is G minus closed. So therefore this correlation function is kind of invariant by this kind of shift, and then next time we will use like explicit form of this psi gamma x to see that that there is a representative that is a holomorphic function. But that requires some preparational work, because I think right now we don't even have like y variables in all this construction, and holomorphic functions should be function of y variables, and y variables will emerge as some kind of Fourier dual to this kind of integer vectors b, so that we can interpret these various states as kind of Fourier components of some function of some additional S1 variables y1 to y capital N, and then the holomorphic functions that will be different representative in QX cohomology class will be precisely these functions of y only. But that as I said, it requires some preparation, and that's why I will kind of spend this next lecture.
Yeah, okay. You see, we almost have the same structure, like deform Q by some cycles, and if we treat this amplitude not for homology class, but first for just chains, and later we can project these chains to homology class. Then we can define some amplitude just like this. I mean, is there any possibility that this structure will naturally gives us a mirror description?
I don't know, because in the case of a Morse theory, it is not true that the amplitude is kind of Q invariant. Oh, okay, maybe amplitudes with G minus are Q invariant. So
yeah, with G minus still it will be Q invariant, but even without Q invariant, we can artificially using the embedding that we can use homology and select representative inside and define some amplitude on homology class.
Yeah, but here we are not deforming by kind of arbitrary classes. So here it is some kind of special divisors at infinity. So that's why it is kind of a different construction.
Yeah.
And it's not just deforming Morse theory by cycles. It's rather kind of constructing X as some kind of deformation of a trivial variety like C star to some power by